Welcome to today's Learning and Retirement presentation. This is the first of 3 talks that will address technologies that are alternatives to fossil fuels. Since, to the best of my knowledge, President Trump has not issued an executive order canceling global warming, this topic remains of transcending importance. Next Tuesday, February 4th, we will hear from Dr. Robert Budnitz, who will speak on the current status and prospects for nuclear power worldwide. The week after, Dr. Ryan Weiser will tell us 5 things you need to know about wind and solar power. It is a great pleasure to introduce today's speaker. Professor Roger Falcone has served as chair of the UC Berkeley Physics Department, president of the American Physical Society, and director of the Advanced Light Source at LBL. He's a member of the National Academy of Sciences. For many decades, we've been told that fusion power is 30 years off. Maybe that is about to change. Roger's going to tell us.
Thanks, Bob. I'm not sure I'm going to resolve the issue, but I will try to say something helpful. Thank you very much for inviting me. I look forward to your questions. I hope my presentation is showing well. Is that okay?
Yep, it looks good.
Okay, great. So my title of my talk is Fusion in the Laboratory and a Potential for Fusion Power. I hope to shed some light on that. I'm going to be mainly talking about a particular type of fusion where we take 2 isotopes of hydrogen and bring them together, and that process releases energy in the form of energetic helium atoms and neutrons. I'm going to talk about a variety of ideas around fusion, but that's kind of a main one. These processes go on under 2 conditions in the laboratory. One, mainly at Lawrence Livermore Laboratory, which is illustrated here, which is something the size of about a centimeter or 2, a little tin can, with a pellet inside that actually is where the fusion happens. And this happens on a scale of a machine that's the size of 3 football fields, but the action happens in something about a centimeter in size. The other extreme of this field of fusion energy happens in containers that are really the size of a house, called a tokamak, and these are called magnetic fusion energy. Princeton has one. Lots of institutions have tokamaks this size. So fusion is a process that can happen on a very small scale, a very large scale. The bottom line is really in the bottom of my slide here, which is, can this process of fusion actually deliver electricity at a cost that is affordable and interesting to people? I show on a plot here a cost per megawatt hour. You could divide that by 1,000 to give you the cost per kilowatt hour. But we see that a lot of energy sources, fossil fuel, wind, solar panels, have been decreasing in cost as time has gone on over the last decade or so. And the question is whether fusion power, when it's ready to get onto the grid to supply power to people, is going to be competitive in this $100 or $200 per megawatt hour, or 10 to 20 cents per kilowatt hour. So some general comments about energy. Energy is plentiful, but there is an increasing need for it because of artificial intelligence needs, computing, countries that are developing. The planet needs more energy. And in fact, it is plentiful. We're surrounded by energy. The sun beams light to us every day. Winds and waves and waterfalls are ubiquitous. Fossil fuels provide chemical energy. And of course, atoms can provide nuclear energy. And there are many types of energies. We're surrounded by it. But to be useful, energy has to be captured or released or converted, typically, because it exists, but we want to put it in a useful form. We want to generate electricity with some other form of energy. We want to store it. We have to provide it in a cost benefit that markets will accept. And of course, energy sources vary geographically, the time of day and year, and by the weather. So what's the main source of energy we're used to? Well, it's fossil fuels, typically, something that burns. And these are based on chemical bonds. And these are the bonds between atoms and molecules that can release energy upon processes like combustion. So if we have methane, there are bonds between hydrogen and carbon that can release energy. And a nice scale for this goes by a physical term of electron volts. And it doesn't really matter how big that is, but it's a small amount of energy per molecule. On the other hand, nuclear bonds, the bonds that hold together particles inside a nucleus, protons and neutrons, for example, those are held together and can release energy when broken, just like in the chemical case. But here they release 1 million times more energy when we break the bonds, when we break apart a nucleus or reform some other nuclei. So there's an advantage in nuclear energy in that it's 1 million times potentially more powerful per atom or molecule than we have out of chemical bonds. And that's what's excited people for decades. So there are two views of fusion energy, I'd say, that the community has. One is this statement from the Princeton Plasma Physics Laboratory, where they operate a fusion machine. It's actually broken now, but that's a subtle point. And they, of course, say that fusion is a process that will transform the planet. And one of the things they show is this graph over here, which is a measure of the success of fusion. It's called the triple product, but it doesn't really matter. It's just some measure of success. And these are all the machines that have been operating for 30, 40, 50 years. And you see this curve is up and to the right. That's a measure of success. They plot it versus this red curve, which is the so-called Moore's law, which is the number of transistors on microchips. So they're saying here that fusion is getting better, just like the number of transistors on a microchip. And we know how much that has benefited society, the fact that we can make more powerful microchips. Fusion is shown here to be as good. Another viewpoint was an article in American Physical Society paper where basically the author points out that a commercially practical fusion reaction will never be made because we've been spending decades and decades of effort and generations of students to try to make it work. It hasn't worked. And this author would show a curve such as shown over here on the right, which is a little bit complicated, but it starts in 2006 and goes down to current days. And it shows you the start and the stop time for the world's biggest fusion reactor in France, the so-called ITER reactor in Ardèche, France. And you see that the time scale of actually getting going and the time scale of when it's supposed to deliver, that's the left and the right of these blue curves, is getting later and later and keeps slipping. And the cost of the instrument that the ITER is illustrated by the size of these green dots here. And you can see that the budget is tripling and then getting 5 or 6 times what it originally was. So this reactor is getting later and later and more costly. And this is part of the reason why people say fusion will never happen. So these two opposite viewpoints are still very prevalent globally. So what are the elements of a fusion energy ecosystem if we could ever put one together? Well, I'll again talk about this deuterium-tritium fusion. Deuterium and tritium are 2 isotopes of hydrogen. They're like hydrogen, just with an extra subatomic particle. When you bring them together and fuse them, they form a new material, helium-4 in particular, and a neutron. These are the particles that come out with a lot of energy. They come out with million electron volts in those units we used before. The helium atom that comes out actually heats the reaction that is going on. It's like the wood burning that keeps wood burning in a fireplace. That energy is deposited back into the plasma, or the material that's causing the fusion. This neutron, this very light particle here, carries away most of the energy, and what we need to do is capture that neutron and turn it into electricity. This is the fusion process that many, many people are betting on. So how do you get a handle on how much energy this really is? Do people see my cursor? I hope they do, if I'm moving my cursor around.
Yes.
Yes, okay. So here's a way to think about fusion energy. Here's a super tanker carrying oil, let's say, and it's in the ocean, and it's displacing 900,000 tons of water because it's a big machine, that's a big tanker that's very heavy. If we took that same amount of water that we displace and pulled the deuterium out, deuterium is this isotope, and a small fraction of water in the ocean contains deuterium, we would get 40 liters, 40 quart-sized bottles of deuterium that could fuel this fusion reactor in a power plant. That 40 liters of deuterium, which is taken out of the 900,000 tons of water, produces as much energy as in all of the tanker's oil that's contained in here. So this gives you a sense that a small amount of fusion fuel could displace, in a power system, lots and lots of oil. So what are the elements of a fusion energy ecosystem? And I have a long list here, and I'm just going to use some words here to say, if we had a fusion energy ecosystem, what would it look like? Well, first of all, there has to be a societal need for it and a technological capability to put it on the grid. And we're in competition with conventional sources and renewables and fission power. Other elements of a fusion energy ecosystem now are, we have an incredible science program, a lot of research that needs to be done. What this means is we have to do research on very high pressure plasmas, which are ionized states of matter. And there are alternative approaches. I'm not going to talk about them much, but since some of them have a connection with Lawrence Berkeley Lab, I thought it was interesting to talk about. Muon catalyzed fusion was something that Louis Alvarez, Dave Jackson got involved with in the 50s. It's not going to make fusion power, but it was a great breakthrough at the time to actually catalyze the fusion reaction with muons, and we could talk about that later. There's the famous issue of cold fusion that Pons and Fleischmann tried to demonstrate in 1989, but they were debunked. You know, if you talk to a physicist now and say, name an electrochemist, the only ones they could probably ever name are Pons and Fleischmann. They're very famous or infamous for this cold fusion that never really worked. And currently, there's a version of cold fusion that our Department of Energy supports called low energy nuclear reactions. It's a new word for cold fusion. And the government funds about $10 million of research in this area. Google has a program in this, MIT, Stanford, even at Berkeley Lab, there's a program in this area. So there are alternative approaches to conventional ones that I'll talk about. In order to get a fusion ecosystem going, we have to achieve net gain. That means we don't put in more energy than we get out. That's kind of a no-brainer. There's all sorts of side effects of fusion energy. We call them neutronics. It's what does the nuclear particle do in a system? We have to breathe the fuel. Those neutrons create nuclear waste, activate and make the parts of the machine radioactive. They damage things. So there's a whole field of neutronics here. There's a fuel cycle. We have to somehow create this deuterium and tritium. We have to recycle and waste products that come out of the device. There's a funding issue, federal, state, commercial, venture capital, philanthropic, public-private partnerships. All of these different forms of funding are pouring money into this field now, and I'll talk about that in a minute. There are things called technology readiness level that our government cares a lot about. What parts of the system for fusion is ready, which parts aren't ready. and they each have TRLs of a different number, 1 through 10, I guess. The materials, the control systems, the lasers, all of that is part of a fusion ecosystem that people worry about. There are supply chains and workforce issues because this is a new technology. There's international collaboration, but also huge competition between countries, which all have different roadmaps. But of course, companies that are going to produce fusion energy are global. So what does it mean to have an international competition? There's a regulatory environment because nuclear power has to be regulated either by local rules or by national rules or international rules. And research and development is being done at our labs, and test facilities are needed. And there's a huge relationship in this field to the stewardship of our nuclear weapons as well. So all these ideas have to be part of a fusion ecosystem, and they're all being worked on. There's some great reports out there. This is a National Academy report from 10 years ago that outlines essentially these elements of a fusion ecosystem. So the Fusion Industry Association is a lobbying group that gathers data and promotes fusion. They pointed out that Department of Energy funds about $1.5 billion last year for this area. And industry has put in about $7 billion. There are 45 companies that are trying to make fusion energy work on the grid. Most recently, these are companies that some of them I'm involved with, that have gotten $100 million, $500 million, $900 million in terms of private funding just recently. So this is a field that's being hugely supported by private investments. The number of startup companies has grown over the last 2 decades. You might say that's exponential growth. I don't know, but they're now over 45 in the current year. The US is the global leader for commuter fusion. We have the most companies, but there are many companies in the UK, Germany, and all the countries that I'm listed here, startup companies trying to make fusion energy work. 4,000 people are working in these companies. There are public-private partnerships that are going on, supported by our government. They go by interesting names, IFE Star Hubs. The University of California just started something called Pacific Crest, which is meant to get state government support for this. Just this week was looked at by our regents. There are programs in Germany and Japan and the UK, all which are public-private partnership based, because the government knows a lot about the research here. Companies have the wherewithal to build the machines. The development of high-temperature superconducting magnets has been a real breakthrough for fusion energy. Fusion energy power scales in a device as something greater than a factor of square. So when you have a more powerful magnet, a superconducting magnet, you can get more power out of your fusion device. And Commonwealth Fusion is a leader in this globally in Massachusetts. They're claiming to build the first burning deuterium tritium tokamak in the US, and they've raised $2 billion from people like Bill Gates. And the other big breakthrough here that was pointed out by the Fusion Industry Association was the demonstration of scientific gain on the National Ignition Facility at the end of 2022. ITER is this program I mentioned internationally. It's the biggest fusion reactor in the world, but it's delayed with higher costs. And if Commonwealth Fusion demonstrates the first burning DT tokamak, it could put ITER out of business. We'll have to see. The U.S. supports this at about $250 million a year. If a private company can demonstrate it first, it's not clear what the future of ITER is. So every country, or many countries around the world, especially those with deep research programs, have their own strategic plan. And these reports here are just the plans coming from the US and the Department of Energy, from the UK, from China, from Japan. These are roadmaps for commercialization of fusion that governments have put together. There's a lot of strategic planning here, a lot of authorization of funding, regulatory reform, and so on, hoping to build regional commercial competitiveness. Every country wants to lead in the fusion energy business. So, nuclear energy, more generally, two types: fission energy, where one atom splits into a larger atom into two or more smaller ones. You'll hear about that in a week or two. Versus fusion, where we join two or more light atoms into a larger one. Both supply excess energy. How much excess energy? Well, this is a nice curve. I think it probably even came maybe from LBL. This is the energy per nuclear particle inside a nucleus. Here it's measured in mega electron volts. So here's all the elements in the periodic table, ranging from the light hydrogen to heavy uranium. So when elements undergo fusion, you go from hydrogen to helium. This is the amount of energy that gets released, an enormous amount of energy per reaction. With fission, this is what happens when you split an element, like uranium. It goes to this two lighter elements. That's the amount of energy released when you go from uranium to the lighter. This is the amount of energy that's released when you go from combining one to something heavier, hydrogen to helium. So it gives you a sense of they have both enormous amounts of energy, fusion a little bit more. Fusion and fission use different fuels. Like I said, uranium, plutonium is used in fission. Hydrogen and related light elements are used in fusion. The byproducts of fission are different. Fission used nuclear fuel, highly radioactive, has to be dealt with in waste. Fusion produces helium. There are some radioactive byproducts, and we can talk about that. But both the fuel types and the byproducts are different for fission and fusion. I mentioned that fission and fusion both put out energy. Fission 1,000,000 times greater per atom or molecule than other energy sources. Fusion a few times more than fission. And finally, where are we in the whole scheme of things with fission and fusion? Fission is in energy production. We have, I don't know, 50, 60 nuclear power plants. I think that's right, Bob. And fusion is still under development. So where does the most important fusion reactor happen? Well, it happens in the sun. In the sun, fusion of hydrogen with hydrogen powers the sun and other stars. The sun is so big that gravity holds it all together, all the fission fuel together, and you get the fusion reaction. The fusion burn propagates out from the center where all the fusion is happening. Gravity is holding it all together, and it keeps going like a burning log for another few billion years. On Earth, it's harder. We don't have a big, heavy sun to power this. Gravity doesn't work here to the extent that it does in the sun. Creating fusion power on Earth is hard, and it in fact requires that you constantly put power in to the system to get it out. So here's a diagram of a potential fusion energy system. There's a fusion reactor here with a little bit of fuel in the red here that's burning, putting out energy. To make that happen, you have to put energy in. So for example, these could be laser beams shining on the center of this target, and we're putting in energy and we're getting energy coming out. So here, the energy comes out. I've illustrated this with a case where we're getting 1,000 megawatts of energy. That's a gigawatt. That's a big power plant. And it's putting out energy, 1,000 watts. We can convert that to electricity by taking those neutrons, putting them in water and boiling the water and turning a steam engine to run a generator. So maybe that's 45% efficient conversion of the nuclear energy into electricity. So maybe we have 500 megawatts of electricity, most of which we can put out on the grid for people. But some of it we have to take, maybe 10% of it, 65 megawatts, to run the system that's going to put the energy back in. So this loop here of conversion of fusion power into electricity, some fraction of it has to go into powering the system to keep it going. If we stop this, if we turn off this switch, the fusion power stops. That's a good thing. It's safe, but it does require energy in and energy out. The hypothesis here is that there's a target gain 160 times more energy out than we put in. That's a hard thing to do. Plausible, but very, very hard. But this is the way a fusion power plant could work. So fusion energy is promising, technically very challenging because of what I just said. It's safer than fission because you can turn it off and it generates less radioactive waste. But there's an engineering challenge here. Can we get much more energy out than we put in? That's the essential challenge of the business. So a very short history of fusion. 20s, Eddington suggests stars drew their energy from fusion. A remarkable thing. We wanted to know how the stars shine. Turns out fusion, and first discussions of it there. In the 30s, we're talking about nuclear fission. So lots of discussion in this time period about nuclear reactions. In 1945, of course, we demonstrated the fission-based nuclear bomb at Los Alamos. In 1949, the Soviet Union developed the fission bomb. President Truman saw that as a threat, so we give the go-ahead to develop the fusion-based nuclear bomb that Teller and company had suggested. At that time, the laboratory at Princeton was established to study fusion. They were thinking about DD fusion, deuterium-deuterium fusion, but they found that DT fusion was 100 times more powerful than that had previously considered, so they started to work on that. Lyman Spitzer at Princeton, when he was on a ski lift, so the lore goes, he noticed how the support cables were twisted around, and he thought about how magnetic fields and magnetic field lines could be twisted around to confine a fusion plasma. And so the Princeton project was then split into two, one for bombs and one for energy. There was something called Matterhorn B project focused on the bomb. That, of course, became classified, moved to Livermore. Matterhorn S project became a Stellarator project, which was the way we were going to make magnetic fusion work before tokamaks. It's now being revived for fusion energy, and Princeton's working on fusion energy to this day. 1985, ITER begins. I'm flash forwarding here through a lot of science, but it was set in motion when Gorbachev proposed an international fusion energy project to Reagan. I was surprised about that, but that seems to be the history. And the concept was to develop fusion energy for peaceful purposes. And here we are now, 2025, 50 companies, nominally billions of dollars of private capital, and the promise by these companies of fusion on the grid by the 2030s. So a very short history of fusion. Of course, fusion was demonstrated 70 years ago, the US fusion bomb, 1952, the Soviet bomb, fusion bomb, 1955. And flash forward to 2022, when the inertial confinement fusion program at Lawrence Livermore, which is a program to support our nuclear stockpile, demonstrated what was called ignition. And that led to the physical review letter, 1,000 authors or so here. But that all happened in this small tin can, centimeter in size. The essential elements of this are 192 laser beams that shine through a hole in the end of this tin can and heated the walls of a gold thimble-sized device that became extraordinarily hot, millions of degrees hot, and radiated onto the fusion target, which is in the center here, this little circular thing, to make the fusion happen. And it's a black body oven that's X-ray hot. So there are roughly three density and temperature conditions that we know about that can cause nuclear fusion. One is I talked about in the sun. Gravitational confinement holds all the fuel together, it fuses, it gets hot. The density is 10,000 times solid densities, temperature 15 million degrees, and the confinement time is hundreds of thousands or millions of years. Magnetic confinement is another way. This is the thing that's going on at ITER or at Princeton. It's extremely low density. It's solid density divided by 100,000, not 10,000 times solid, but 100,000 times less than solid density, very like a gas. The temperature is hotter, 150 million degrees, 10 times hotter, and the confinement time is measured when it's reported in seconds, but it could be hundreds of seconds or thousands of seconds. Inertial confinement is what goes on at Lawrence Livermore, where a laser the size of a couple football fields, all those lasers are focused on this thimble-like device. They create conditions that are 1,000 times solid, 10 times less than the sun, but still pretty dense, 150 million degrees, like the tokamak, magnetic confinement, but the confinement time is only tens of picoseconds. So that's why it's called inertial confinement, because it only holds together for picosecond, which is a millionth of a second. And then it explodes. So it's only inertially confined until it explodes. Another way to think about these devices is that there needs to be a temperature and a pressure and a confinement time to make fusion work. In magnetic fusion, the density is very low. For those of you who think about particles per cubic centimeter, it's 10 to the 14, confinement times in seconds, but it's hot, so the pressure is very high. It's 10 atmospheres. So the pressure time product is 10 atmosphere seconds. Similarly, at Livermore, where this football-sized field of lasers focuses on a small thimble, the plasma is confined by inertia. The densities are very high, 11 orders of magnitude higher than magnetic fusion, billions, tenths of a billionth of a second, pressures at 100 billion atmospheres. But again, pressure time is 10 atmosphere seconds. And that tells you something about the reaction rate. We have to have a certain density of particles in a certain time for enough reactions to happen to make it all worthwhile. That's why pressure times time is so important. It happens at other places, this as at Sandia and at a laboratory at the University of Rochester, where we also do this, but it's pretty much just a couple places around the world where this all happens. So why do we need high temperatures and densities? And so the way to think of this is that the two nuclei here, deuterium and tritium, are positively charged. They want to repel each other. So there's a so-called Coulomb barrier that prevents the two nuclei from getting close enough to each other that they will react and grab each other's nuclear particles. And there's a repulsive force called the Coulomb force that wants to prevent them from coming into contact and fusing. What's needed is that the temperature of the particles, or the energy that the particles have, be very, very high so that they can crash into each other and not be repelled. They go up this Coulomb barrier and they get close to each other. And that takes temperatures of, say, 10 kilovolts in energy. That's very, very hot, millions of degrees. When it happens, those two particles slam into each other, the deuterium and tritium, and they fuse, producing this helium and a neutron. And these particles come out with energy as well. They come out with this 10 mega electron volts. So this tells you something. If the particles are coming out with, say, 14 megavolts of energy, but they had to come in with 10 kilovolts of energy, that tells you that the maximum amount of gain you can get out of one reaction is 1,000. And that is true. That's sort of a physical limit on how much energy you can get out. From a engineering perspective, we probably will never get that fundamental amount of energy out, but who knows? Okay, so this capsule is heated. I'm going to speed up a little bit here. There are two main techniques that companies are thinking about. I'm just looking at the right-hand side here, where we bring laser beams in, hundreds of laser beams. They either are shining on the wall of this thimble-sized capsule that makes a very hot oven that then radiates onto the surface of this sphere, and the surface of the sphere evaporates and rushes out, explodes. It's an action-reaction. The material that is evaporated off the surface here comes off like a rocket, compressing the target to very, very high densities and temperatures. We can also take the lasers and shine them directly on the target. That's called direct drive. Two major ways companies are doing this is either direct drive, shining lasers on the capsule, or indirectly. And the rocket that comes off is incredibly powerful. It's doing 200 miles per second of ejection of surface material that's being blown off here and compresses it to 100 billion atmospheres. So the history of those hull rooms, they're called hull rooms, these devices that hold the capsule inside it, and it goes all the way back to the days of the original nuclear weapon. This is probably the only diagram that can be shown, where there's a primary weapon, which is a fission weapon driving in a box called the hull room, a secondary material, which is the hydrogen bomb. In 1960s, John Knuckles at Livermore had the idea, well, not to use a nuclear bomb to power this, but maybe there's some other drivers, an accelerator, a charged particle beam, lasers, something to put energy into this capsule here to make the fusion happen. And then in the 70s, much more sophisticated devices that look a little bit like present day devices here, that are the cans that contain the fusion, were being worked on here. So there's a long history of this field of hull room drives. Okay, so I just want to say something about the net scientific gain that we have right now. So Livermore demonstrated what's called scientific gain in a system in December of 2022. How did they do it? Well, they stored electrical energy in capacitors of 400 megajoules. Though that energy was dumped into flash lamps that drove lasers, powerful lasers, which are this purple material here. That 400 megajoules of electrical energy produced 5 megajoules of laser energy, which we had to change the color of those lasers through frequency conversion to only produce 2 megajoules of energy. That 2 megajoules of energy was put into this small tin can here that contained the fusion capsule, which is shown here, and only 0.3 of a megajoule of energy actually goes into the capsule. And into the implosion in this very center of it, 25 kilojoules or 0.025 megajoules is actually deposited there. So a lot of loss of energy from the start. Out of this came 5 megajoules of fusion energy from 15 micrograms of deuterium tritium. So fusion gain was claimed, or so-called ignition, because 5 megajoules came out and 2 megajoules went in. This was a requirement of the National Academy of Sciences for ignition to be declared. We didn't go all the way back to the capacitor banks. So this system could never make a power plant because there's 100 times more energy going in than coming out. But it was a proof of principle that maybe we could get there. If you don't think about megajoules, you think about donuts and calorie value. NIF put the energy in 2 donuts into the capsule, and they got out an apple fritter and donut worth of energy, calorie value, a little more energy in the apple fritter. And this is one way of thinking of the amount of energy actually in megajoules. It's 2 donuts. This program actually was put together to support our nuclear stockpile. I think I want to move to questions very quickly, so I'm not going to dwell on this, but it was never a fusion energy program. It was always a program that was supporting the fact that we gave up nuclear testing in 1992 if the laboratories could do nuclear tests above ground without a high yield shots. I'm going to skip this because it just shows the power plant, but maybe the diagrammatic nature of what a fusion power plant would look like driven by lasers is good. We have a reaction chamber, a big chamber, maybe the size of a house. We have a target factory that produces these little beads of deuterium and tritium. We have a whole bunch of lasers on the outside of this reaction chamber. They all shine into the chamber. The target gets shot into the center. The lasers shine onto the target. It burns and puts out fusion nuclear particles. Those particles then generate electricity by making steam from their high energy and their heat, producing electricity on the grid. Some of those neutrons have to be used to breed the tritium. The tritium comes from a lithium wall, a liquid lithium wall that surrounds this whole device. When neutrons hit lithium, it breeds tritium. That has to be extracted for a fuel for later on. And for net power, all of these different engineering systems I've shown here have to be engineered, and that's the challenge. There are many different fusion drivers that are all illustrated here. They're kind of neat. This one's a tokamak over here with a central plasma core and some magnetic fields. This is a chamber. The middle one here is a chamber with laser beams shining in that I just showed you. That's a possibility. Commercial companies are working on all of this. This is an interesting system. This doesn't use lasers or magnetic fields to confine it, but it uses mechanical energy. It has pistons that slam metal, liquid metal, into a target here. And megajoules of energy from compressed pistons can compress the target. I don't really believe it's going to work, but it's attracted venture capital funding. This device here is the original Lyman Spitzer stellarator, a very complicated system of magnetic coils. It's like a Mobius strip that confines the magnetic field and the plasma, which is the yellow thing in between. It used to be too complicated to ever work, and so work was stopped on it. But now we have great design tools for engineering such things, and we believe we have the capability of designing it. So this has spun out several companies to hold the plasma in this stellarator type device. And this is an interesting device being made up in Seattle by a company called Helion, and I'm just going to talk about that for a second. It's an interesting device. The company is called Helion. I've gone up there several times. It's interesting because it's supported by someone named Sam Altman, who you might know is from OpenAI and invented ChatGPT. He's a billionaire, and he's put billions of dollars into this field of this company, Helion. It's a plasma device called the field reverse configuration. And if you follow these numbers, 1, 2, 3, 4, you get a sense of what happens. It creates a plasma. It forms a plasma in these sections 1, and it's these pinkish dots here that are the plasma, and they're spinning. They're then accelerated by magnetic fields. These coils that are wrapped around it propel this plasma. It looks like a smoke ring. In fact, it's kind of like a smoke ring from someone blowing a cigarette smoke ring. And it's propelled toward the center. And when it hits the center, it's compressed by more magnetic fields. And then they have an interesting way of generating electricity because the plasma here is full of charged particles. It's inertially confined for microseconds, but then explodes. And as those charged particles escape, the same coils that propelled the plasma pick up the charge current and directly put it into electricity because it's like a moving coil, and it generates electricity just from the high current of the fields. It's an interesting device. They're the company that quote, they will deliver at least 50 megawatts of power and produce electricity by 2028. And they've signed a contract with Microsoft to deliver fusion power to them. So they're the most aggressive, I would say. And Sam Altman needs the power for AI. So other fuels are being used. I talked about DT fusion. There's DD fusion. There's proton boron fusion, D-helium-3 that Helion is using. But if you look at a curve of the cross section for the reaction versus the amount of energy it takes, this is a cross section, and you see that the cross section for deuterium-tritium is the highest of all of these other fusion reactions, and also peaks at the lowest energy. So that's why everyone likes DT fusion. But these other fusion reactions can still work. They just have to be hotter because they have to be to the right. And the cross sections aren't quite as high as DT. But people are still betting on those other reactions because in the case of D-helium-3, the main product is not a neutron. And it doesn't, and without neutrons, you have a much safer, less radioactive device. There are optimum temperatures for all of these things. So I'm going to finish up here and say the concepts for fusion energy are being explored. We've talked about magnetic confinement, tokamaks and stellarators, and field reverse configurations. And then there's the inertial confinement for pulsed implosions of plasmas, indirect, direct drive. The targets are very important. The concept here is called wetted foam targets. These are like targets made out of sponges, and liquid deuterium-tritium is soaked into the sponge. That's important because currently the targets on the NIF laser cost close to $1 million each to make. In order to make electricity at 10 to 20 cents a kilowatt hour, that $1 million target has to be reduced to about 50 cents per target. So we got 6 orders of magnitude in cost to come down. We have to figure out a cheap way to make those targets work, and wetted foams are the concept here. There's an interesting idea here, low power lasers coupled to build-up cavities. We could talk about that. It's by a Nobel Prize winner who invented the blue LED. It's a crazy idea, but we could talk about it if someone's interested. Alternative concepts are low energy nuclear reactions, so-called aneutronic fuels, these fuels that produce fusion without neutrons, and more environmentally safe. And the whole concept of liquid lithium walls is very important to protecting the fusion reactor. So I'm going to end on my final snarky perspective on fission and fusion and mitigating climate change. So fission is great, but you know, we got a lot of radioactive material buried in the ground. It's what keeps the earth warm down deep. And if all we do is tap into the geothermal power, this is a shielded fission reactor down there. Sounds like a pretty good idea without having to deal with the fission power plant problem. Fusion, another good idea for energy. However, the sun's a great source of fusion energy for photovoltaics and wind power, and it's safely, again, not shielded, but it's 90 million miles away. So maybe that's a better alternative. This is a gigawatt solar power plant on 500 acres. And finally, we're all interested in carbon capture to try to deal with the amount of carbon we have in the atmosphere now. I'm kind of a fan now of biochar. I realize it's a little bit difficult, but photosynthesis has captured and sequestered carbon, greenhouse gases for billions of years. And if we use biomass and we capture it, convert it into biochar by thermal decomposition, pyrolysis, this is now stable carbon that can be buried for a long time. So I think if one was a contrarian, one would offer up underground fission, solar fusion, and photosynthesis for carbon capture. And on that, I want to thank you and ask for your questions.